Okay, good afternoon, everyone. Very welcome. It's a great pleasure to be here, and I would also like to thank the organizers for the invitation. According to the registration list, people here have a very different background, and they are also from different academic level. So my goal today is to give a rather high-level overview of how we can look at distributed learning from a multi-agent perspective. I start from the very basic, and towards the end, I describe some materials which are a bit more involved. Well, as a gentle start, let's see a very basic machine learning program. We have a data set consisting of n data points. Each data point has two elements, x and y. X is the feature vector of that data point, and y is the label of that data point. When we do machine learning, we train a model with some parameters theta, and we hope that when we receive some unknown sample, we give this sample to this trained model, and the trained model gives us the output, the y, with hopefully high accuracy. Machine learning algorithms are often iterative. This means that they update the parameters over and over until they achieve some optimality conditions. And compared to the classical optimization, they have some characteristics. For example, they are more fault tolerant because they do this iteration, and if some error occurs in between, they can correct it over time. They depend on the structure of parameters. If there is some relation between the parameters, such as causality, dependency, or correlation. And they might have non-uniform convergence rate for different parameters. Now, machine learning can become computationally expensive. And why this is the case? First, because we have massive data, which might not be that rich in information. We have often high-dimensional feature vector. The models can be very complicated with several parameters. There can be some bottleneck effect if we do this in a centralized manner. There can be lack of generalization to new methods and new models, etc. One important way to address at least some of these issues is to run the machine learning program on different devices and different learners, different servers. And we can look at this from different perspectives. One perspective is the aspect of control systems, because we have different systems that work collaboratively to achieve a common model. And what the control theory or control aspect or control perspective covers is what is the effect of the structure of this collaboration on how it performs. We can have different structures. For example, it can be via central controller. It can be totally ad hoc, where several devices or learners can communicate pairwise. And it can be a sort of hybrid of the both. So with some small controller and one big central controller in between. From the core machine learning perspective, we can look at it depending on if we divide the data between different servers and different learners, or if we divide the parameters between different learners and different servers. I come back to the control aspect later. First, I will describe the data and model effect. So if we divide the data between different learners, we give each of the learners a subset of data, like as I have here, D1, D2, D3, and so on. And all of them train the same model, but using the data that they have. And at the end, they share the models that they have to achieve or aggregate them to one single model. The questions to answer here are two things. First, how do we divide the data between different servers? And second, how they share these local models with each other. And this is where actually control aspects play a role, because with considering different possibilities for dividing data and sharing the model with each other, then we can call this collaborative learning paradigm different things, for example, federated learning. And if you want to divide the model, we give the same data set to all of the servers, to all of the learners, and each of the learners train a subset of the parameters, given the whole data set that we have. And at the end, they again share the parameters together. But this one is a bit more complicated, and it might not be always applicable or implementable. Okay, so far I described a very basic of distributed machine learning. Now the question is, how can we implement distributed machine learning in the computation infrastructure? And for that, let me start to explain the computing hierarchies. The highest layer is the cloud. The cloud has a large number of high-capacity learners, servers, and high-capacity data centers, which are all collected at a location far away from the network. So if you want to do machine learning on this cloud, we send all of the data to the cloud, and then we get the model back. Then the second layer is fog. Fog has a larger number of data centers and servers, but with lower capacity. And these are all distributed in the area between the cloud and the edge network. And the lowest layer is edge. And thanks to the advances in the hardware, edge devices, which are actually all of the devices that we see, like mobile phones, laptops, etc., have some computational capacity. Of course, it is way less than the servers or data centers, but still they can take some part in machine learning. Now, the question is, how do we take advantage of edge and fog in addition to the cloud? If we use a cloud, as I said, we need a lot of energy and we need a lot of time because the data has to travel all the way to the cloud center, but we have high computational power there. However, if we delegate some of the learning tasks to edge and fog, we can save a lot of time and energy because the data doesn't travel that long. And besides, it is more secure and this is more private. But at the same time, we have also some challenges. For example, it can happen that multiple models are offloaded to one learner. So each of them gets only half of the resources, or they have to make a queue because there is not much computational power. The devices are heterogeneous, and therefore we will have some straggling effect, meaning that if one device hasn't finished learning, all other devices has to wait for it in collaborative learning. Or there can be multi-party usage in the sense that each party has his own interests. There can be different service providers, etc., that might complicate the learning. And if we look at it more carefully, we see that most of these problems somehow boil down to the resource allocation problem. And when we want to address these resource allocation problems, we face some second-order difficulties. And those are, for example, lack of the information. So there is some uncertainty, lack of a central controller who doesn't have the information of all of these devices. For example, what is their computational capacities? They can be resource scarcity, the network at the edge is very fast varying, the topology changes over time, etc. Now the question is, how do we address these problems? If we want to do some distributed machine learning at the edge of the network with different devices. In this case, actually the distributed learning sort of boils down or can be casted as a micro-tasking or the crowdsourcing, where we have different crowdsourcers with multiple projects and different workers, and each worker can select to which project and how much to contribute. In this case, there can be some competition between the crowdsourcers to attract the attention of the workers. And there can be also some competition between the workers to be working on a well-received project or to attract collaboration to some specific point. Because the collaboration is less than something, it can happen that the task is not done. If the number of collaborators is more than something, the utility per collaborator reduces. And all of this can be modeled as a multi-agent system. In a multi-agent system, we have different large number of probably decision makers. Each decision maker has some capacity, some type, has some knowledge, and has some objectives. Given this knowledge, capacity, and objectives, the decision maker takes some action based on the action set that they have. Now, if we look at it from the distributed learning perspective, each of these agents is a machine, is a server, is a handheld device, is a edge device who can decide if he or it wants to take part in the learning process or not, and if so, how much is the resources that he wants to contribute to this learning process. The hope in the multi-agent system is that the agents interact with each other, and at the end, they arrive at some solution which has two characteristics. First, it should be stable, meaning that the agents wouldn't want to change their action anymore. And second, it is efficient. In different sense, it can be in the sense of aggregated utility, so that all of the players together get the highest utility. It can be in terms of fairness, so that all of them get almost the same utility, or maximum fairness, etc. And we can model different scenarios. We can model competition with such multi-agent systems. We can model cooperation, etc. For example, in a competitive model, the reward of each action reduces if multiple players select that action, often as a decreasing function. I just made an example. If different learners get the same task, if a different task is offloaded to the same learner, then the learner has to divide the resources to different tasks. And therefore, those tasks or those crowdsourcers should compete over the resources. And there are also many different scenarios in resource allocation. In cooperation, it's different. In cooperation, it's usually beneficial if there are more resources and more players are involved, because, for example, the cost is shared. So if multiple learners are interested in one single model, it is beneficial for them to divide the cost of learning between themselves. So both competitive and cooperative models can be used to model distributed learning at the edge. It depends on the scenario that we consider. So after we model the problem with multi-agent system, the next step is analysis. And for analysis, we can use game theory. Game theory has two branches, non-cooperative and cooperative. But in general, it's a mathematical tool to solve conflicts. Here, for example, first I discussed a non-cooperative game. As you see, I have two players. Each player has a set of actions, so player 1 A and B, player 2 C and D. And as a result of every joint action profile, each player gets some utility. For example, here A and C results in the utility 0 for one player and utility 2 for another player. This game can be done in one shot, in the sense that each of the players selects one of this action, and then as a result of joint action profile, each one of them receives some utility. Or it can be done in a repeated manner. If it is done in a repeated manner, then there is some possibility for learning, meaning that the players can use the historical action and rewards to hopefully settle at some point that is not only stable, but is also beneficial for both of the players, or it is more fair. In the cooperative setting, the player cooperate in doing one task, and there are different formats for this game, for example, coalition formation, bargain, etc. One of the most important ones is coalition formation, in which, as I said, they make different groups. In each group, one task is selected based on the opinion of the member of that coalition. After doing that task, they get some utility. This can be either transferable between learners or non-transferable. And given this utility, there are some ways to sort of evaluate the performance of that cooperation. Okay, so far what I did was that I described the distributed learning paradigm, the computational hierarchies, and I said that if we want to implement distributed learning tasks at the edge of the network, we can take advantage of multi-agent systems, followed by the analysis using game theory to solve the challenges that arise there, especially concerning the resource allocation. Now let's see an example. And I use federated learning as the example. I consider this as a distributed learning paradigm. And what happens in federated learning is as follows. We have different data owners, which are called clients of federated learning. And this data often is already there, so it is not the case that we necessarily divide the data and give to them. Rather, the data owners themselves collect the data. And there's a central unit, as you see here. So all of these clients train the same model. They send the local models and gradients to the central unit. And central unit does some aggregation. For example, it does a simple average and send the gradients and the global models back to the data owners. The data owners do the optimization again and send the local data back to the central unit, and they receive the global model, and it continues iteratively until some conditions is satisfied. And usually that condition is defined based on the difference between global model and the local model. Now, assume that we want to implement federated learning at the edge using the edge devices. If a device participates in federated learning, then it can take advantage of the model. It receives the global model. And it can happen that several devices want to participate in federated learning, which is not always possible. A very intuitive reason is that there is not enough communication resources for that. So a subset of the clients should be selected, and this is called the client selection problem, which is a research topic in federated learning. There can be a centralized solution in the sense that we assume that there is some central controller who has the entire information and selects each subset of clients, potential clients, take part in the federated learning, or we can do it in a distributed manner, which means that we assume that the central unit allows the interested devices to be self-organized. That is, they can decide if they join federated learning, and if they join federated learning, to which model they want to contribute and how much resources they want to put into it, and so on. And if your model is like this, it is as if you have a distributed multi-agent system, because each of the client, there is an agent who can decide based on its own capacity and preferences and objective how much to contribute to federated learning. So we can use the game theory to model the participation problem in federated learning. Then, okay, how then the model look like? As I said, the clients is a player, each client is a player. Each player autonomously decide about the action. The action includes the project or model to participate, the allocated computational and sensing capacities, and the other clients to collaborate with. And then in this model, in addition to what is the agent and what is the action set, we also need to define the reward and cost. And the reward and cost usually is defined based on the factors that consider as the performance metric in federated learning. For example, the model accuracy, the transmission cost in terms of resources, the convergence delay, and other factors. And then we can model it both in a cooperative manner or in a non-cooperative manner, depending on the scenario that we consider. So if we consider a coalition formation framework, we assume that the clients want to make coalitions. Each coalition selects one model for the federated learning. And based on that, they receive a reward, which is the model improvement compared to the local model. And it can also include negative aspects, such as the consumed resources. And the goal is to involve those clients that they are good clients, that they can contribute well to the federated learning. So they have good data set, they have high computational power, etc. And we can also model it in the non-cooperative framework. So in the non-cooperative framework, the potential participants act as non-cooperative players. Each participant decides on a model based on his preferences and interests, and the joint action profile that they select, they result a reward for each player. So if, for example, a very few number of participants decide for a model, it can happen that the model is not accurate enough. If too large number of participants decide for a model, it can happen that the data becomes too diverse, so it can be not exact enough for each of the clients that take part. But in either cases, they do this repeatedly until they hopefully settle at some efficient, stable point as I described before, that we need to have as the outcome of the interaction in a multi-agent setting. Okay, good. One more point that I should say is that here when we say cooperative and non-cooperative is based on how they strategically act. Still, it is collaborative machine learning because they, at the end up to come up with a single model altogether based on the data that they have and based on the computational power that they have. But it is about how they act strategically in this system because they have different interests. Now, okay, so far what I said was that we have multi-agent system which is used to model the distributed learning paradigm, and that multi-agent system can be analyzed using game theory. But game theory or classical game theory is not always sufficient. It is, okay, it's not exact, like it is applicable, but it's not always sufficient. And the reason is that in classical game theory, one assumes that the game matrix or the outcome of every joint action profile is known to the player beforehand. So every player knows that if I select, for example, action A and he selects action B, then I receive the utility 1 and he receives the utility 0. And what they try to learn over time is that a stable, efficient point, not the utility of the joint action profile. But it can happen that even the utility of every joint action profile or the utility of every coalition or the type of the other agents, here, for example, the computational capacity or the preferences is unknown. And the question is, how do we address this? Because here then, game theory alone is not sufficient. And to address this problem, we can integrate learning methods, for example, reinforcement learning, into the decision-making strategies. And then what happens is that players play the game repeatedly, and at every round, they not only select for some action that hopefully results in a stable, efficient point, but also they try to infer some understanding about the unknown variable in the game. For example, the type of the collaborators or the preferences of the collaborators. For example, here I have a non-competitive case, and this is something general. I mean, it can be applied regardless of it is a distributed learning task or some other thing. So in a very abstract form, I have a number of decision makers, and those decision makers do not have any idea that what is the outcome of every joint action profile. They want to take actions over and over, observe the actions of each other, and also observe the reward. And they hope that at some point they converge to some steady state and efficient point. So how should they make decision? And this figure shows how, I mean, it's a very high level sense, how they should make a decision. So it consists of two parts, which is more learning, and one part which is more game theory. So first they observe the historical reward, and they then use some regression method, for example, to estimate the reward of every joint action profile. And from the other side, they observe the historical action, and then they try to predict the joint action profile of others. So at every round, I have, as a player, I have some historical reward. I do regression, I come to the conclusion that what would be the outcome of a joint action profile. And from the other side, I have observed the actions, and I have some feeling how would the others play. And from these two inputs, I estimate what would be my best response to this, what would be the action that maximizes my utility, given these estimations that I have. And I play with that action with some high probability, best response dynamic. And I also select some action at random just to gather more information with a very low probability. And this scenario can be shown that under reasonable conditions, of course, like I'm not talking about the mathematics, but it can be proved that under reasonable condition, this entire decision-making scenario, if used by all of the agents, results actually in a good performance, both concerning the utility of the players and also the convergence. So it converges to a STD state in some sense. And as I said, so this action can be anything. They can be, these decision makers can be clients of a federated learning model that want to decide in which model to participate and how much effort put into that model. So everyone thinks that what has been the preference of others, and based on that, it decides which which model to take part. And of course, a similar thing can be done also in the cooperative setting. In the cooperative setting, I have also an example here. Here is, of course, very important what is the capacity or what is the type of the collaborators. If I want to make teams, of course, I pay attention how good are the teammates. But this information is often uncertain. So this information is often private. And therefore, if I want to make good coalition over time, I need to learn or I need to infer the type of the collaborators. And how this can be done? This can be done by integrating some learning method. Here I'm doing some Bayesian belief option update into the coalition formation setting. So what I do is that I first start with some initial belief, and then I make coalitions with the agents, and at every coalition formation, I observe the type, a realization of type, and the outcome of the coalitional action. And based on that, I do two things. First of all, I update my understanding about the outcome of the coalitional actions, and second, I update my belief about the type of the players, type of the other collaborators. And the next iteration, I again make coalitions. Based on that, I observe some information, and again, I update my belief until I converge to some stable point. Okay, good. Yes, to sum up what I did. First, I described very basic of distributed learning. And then I described the computing hierarchies. So I explained that the distributed learning can be implemented between the edge devices. The characteristic of edge devices is that they belong to different parties. They are not necessarily motivated, or they do not have necessarily the incentive to put all of the efforts in a specific task. They act basically based on their own capacity and knowledge, and therefore we can model a problem of the control of distributed learning over edge with a multi-agent system. Then I said that, okay, this multi-agent system can be analyzed using game theory. It can be a cooperative game, it can be a competitive game. The matter is that how we model it. And for the model, we need a set of agents, we need to define a set of actions, and we need to define the reward and cost. And some assumptions, how do they would take part in this participation, in this learning. And then I also made an example about federated learning, how federated learning can be a multi-agent system. And finally, at the end, I discussed how do we address the uncertainty in this with two small examples. What are the possibilities of still using multi-agent system and still using game theory, even if we have to assume that some information in that model that we have developed is absent. So, okay, all of this said, the fact is that mathematically, it is very feasible. So it can be just considered as an abstract model, and it can be analyzed, and on paper one can converge to equilibrium, etc. But of course, implementation, it's different. It is not that straightforward. Even if you have the proof on the paper that it will converge, it might not in the hardware. So there are some challenges to address. First of all, the convergence to a steady state is not guaranteed for many scenarios that actually arise in real-world applications. Or in other words, not all real-world applications are one-by-one modelable using multi-agent system. There can be a slow convergence to the equilibrium, which is on paper no problem, but of course in the real implementation it causes problem. It can be complex. It is difficult to integrate humans into the model. There are a lot of hardware constraints because even right now, the hardware is not that capable of processing and reasoning and taking actions. And of course, there can be legal regulation. So if we are assuming that multiple devices participate in the collaborative learning and they want sort of reimbursement for the effort, how one can really realize this apart from modeling. And specifically, it becomes more difficult when there are the increasing number of agents and action. And by agents, of course, in the discussion today, I mean the number of devices at the edge that would participate in collaborative learning, and the actions, the number of models, and possible learning projects. Okay, and actually there are several SOA solutions, both in the abstract sense of decision making and also in terms of a specific distributed learning. For example, federated learning using analysis of federated learning using game theory. But as I said, hardware-wise, most of them are not suitable for such on-device intelligence implementation. Okay, good. That was it from my side, and I'd be glad to answer the questions. Thank you very much.